Hi, we're Group 4 and this is our third year project for curves and surfaces.
Hi, I'm Alice and I'll be talking to you about the plane curve.
Hi, I'm Joel and I'll be talking about the space curve.
I'm Helen and I'm going to be covering the first part of the surface.
And I'm Hayley and I'll be covering the second part of the surface.
This is the equation that we have for our plane curve. You can see from the model that we have made what the plane curve looks like. This is the definition that we have for a curve for it to be regular. From the equation of gamma shown before, we can calculate the first derivative shown here by first calculating the derivative of the x component with respect to t, and then secondly calculating the derivative of the y component with respect to t. The norm of the first derivative is the speed, which we calculated as this. And we can see by looking at the graph of sine of 3t that if we restrict the domain between 0 and pi over 3, then it will be positive, which was highlighted in green. We can see that when t equals 0 and pi over 3, that the speed will be 0, which is not regular, but because we want our plane curve to be regular, we need to restrict the domain between 0 and pi over 3 to make our plane curve regular. The curvature for a plane curve is defined as the following equation that we have. The curvature basically is how much a curve curves, and it measures how much the tangent is changing. So we can find the second derivative by differentiating gamma prime. By plugging in all components into the curvature formula, we have found our curvature to be the following. As we have restricted to the domain between 0 and pi over 3, we know that this is positive, and so the curvature is positive, so it simplifies down to the following. We can see from looking at our model that when t equals 0 and t equals pi over 3, the curvature is undefined. When we look at t equals pi over 6, which is roughly about here, the curvature equals 4, which is the smallest curvature. And then as it gets closer and closer to 0, t equals 0 and pi over 3, the curvature increases until it reaches 0 and pi over 3, where it becomes undefined. So next we are going to look at the sine curvature, which is the direction that the curve moves. If the sine curvature is positive, then the curve moves towards the direction of the normal. However, if the sine curvature is negative, then the curve moves away from the normal. We can see that our sine curvature is the following when we restrict it between the domain 0 and pi over 3. So we have that our sine curvature is positive, so the curve moves towards the direction of the normal.
This is our space curve. You will notice the similarities to our plane curve in the xy components. However, in our space curve we have a z component, which is sine of 3t over 3. We're now going to see if our space curve is regular, and we previously discussed what it meant for it to be regular in our plane curve. This is our gamma prime of t. The x and y components are the same as our plane curve, however we've now to differentiate our z component in terms of t, which equals cos of 3t. To check whether it's regular, we calculate the speed, which is the norm of gamma prime of t. We take the sine of 3t from our plane curve and we square this, and then we also square our z component, which gets cos squared of 3t. From the identity we know this equals 1, which does not equal 0 for all of t that exists in the real plane, so therefore we know that this plane is regular. We can now calculate the curvature. This is our formula for curvature when working in R3. The formula is the norm of the cross product of gamma prime and gamma prime prime divided by the norm of gamma prime cubed. From what we calculated previously, we know that gamma prime equals 1 for all t, so our curvature now equals the norm of gamma prime cross gamma prime prime, where gamma prime is our first derivative of our space curve, which you showed earlier, and gamma prime prime is the second derivative of our space curve. The second derivative is the same as the plane curve. However, we've now added our z component, which is the second derivative of the z component, which equals minus 3 sine of 3t. We have now calculated our curvature for our space curve. This equals the square root of minus 56 cos to the power 6 plus 384 cos to the power 4 minus 144 cos squared plus 25. We then plotted the graph to see how the curvature varies. The graph clearly shows that the curvature varies between values of 3 and 5. The greatest curvature of 5 is achieved when t equals pi over 2, and the lowest curvature of 3 is when t equals 0. As the curvature does not equal 0 anywhere, we can now define our space curve as a Frenet curve. This is because the curvature is nowhere 0 and it is regular. We're now moving on to calculate the torsion of our space curve. The torsion of a curve measures how sharply it is twisting out of the xy plane. If the torsion equals 0, it is a plane curve. We will now show that the torsion does not equal 0. Our formula for torsion equals the inner product of gamma prime cross gamma prime prime, which we used previously for the curvature, inner producted with gamma prime prime prime, which is the third derivative in respect of t for our space curve, divided by the norm of gamma prime cross gamma prime prime, which again we already calculated, so we need to square this on the bottom of our fraction to equal our torsion. We have now calculated our torsion for our space curve, which you can see the answer above the graph. We then plotted this to see our range of values of the torsion. The values go between 8 and minus 8, with the greatest torsion being when t equals 0, and the lowest torsion of minus 8 being when t equals pi. The torsion equals 0 at pi over 2. This is obviously when we are equal with our plane curve. We are now going to see how our plane curve relates to our space curve. As you can see from our model, our space curve retains the general shape of the plane curve. Also, as Alice said, the curvature of the plane curve is symmetric through 0 and pi over 3. The space curve's torsion is symmetric through 0 and 3 pi over 2, and our curvature is the same, is symmetric through 0 and pi over 3, which is the same as our plane curve. We're now going to move on and talk about our surface.
Our surface is given by the following equation. We've chosen u and v to be greater than 0. This ensures that x is bijective. Since each component is a polynomial and it's stated that u and v cannot equal 0, they must all be continuous. This implies that both x and the inverse of x must also be continuous. Both of these pieces of information show that x of u is a surface patch. We've plotted x with the parameters u and v constrained to minus 0.9 and 0.9. Using an increased range, you can see that the fractals change it to the following. We've calculated the coefficients of the first fundamental form using the formulas seen here. xu represents differentiating x in terms of u. This is the same for xv. These are our answers for E, F and G, each represented as a graph. The plots of E and G are very similar, with a very large increase around the origin and the value of 0 as u and v move away from the origin. Capital F has a different plot. This is valued 0 around the origin, then as u and v move away, the functions fluctuate from a very large negative number to a very large positive one. These coefficients are used in this formula to calculate the arc length of a curve gamma on our surface. Haley will later show that this curve gamma lies on our surface. The coefficients of the second fundamental form were calculated using these formulas, where nx is a Gauss map, given here, xuu is differentiating x twice with respect to u, same for xvv, and xuv is first differentiating x with respect to u, then with respect to v. Here are our solutions for E, F and G. The shape of all three are the same but orientated in different directions. We use the coefficients of the first and second fundamental form to calculate the Gaussian and mean curvatures. Those formulas are given here. The results can be seen here. Since our surface has mean curvature that equals 0, it is called a minimal surface. This means it minimises the surface area. You can see that the Gaussian curvature will always be negative or equal to 0.
We can see that our space curve lies on the surface by considering the parameterization demonstrated by the following diagram. By plugging in u of t equals cos t and v of t equals sin t into our surface, we obtain the exact equation for our space curve. The normal curvature of a curve is defined to be the curvature of the curve projected onto the plane containing the curve's tangent and the surface normal. We have calculated the normal curvature using this formula: Kn equals E u dash squared plus 2 F u dash v dash plus G v dash squared, where E, F and G correspond to the coefficients of the second fundamental form, and calculated it to be 4 sine 3t. The geodesic curvature is the curvature of the curve projected onto the surface's tangent plane. To calculate this, we have used the following relationship: k squared equals kg squared plus kn squared, and rearrange this formula to obtain kg equals the square root of k squared minus kn squared, where kg represents the geodesic curvature, k represents the general curvature, and kn represents the normal curvature. We calculated this to be the square root of 15 minus 6 cos 60 for our surface. As Helen previously mentioned, our surface has mean curvature of 0, demonstrating that it is a minimal surface. A minimal surface implies that the surface is shaped like a soap film, a bit like when you blow bubbles through a plastic stick as a kid. The first research on minimal surfaces dates back to 1768, when J.L. Lagrange was trying to solve the following problem: find a surface of least area stretched across a given closed contour. Assuming that the surface is in the form z equals z of xy, Lagrange showed that zxy must satisfy the following Euler-Lagrange equation. Later, in 1776, G. Monge discovered that the condition for minimizing a surface leads to the condition that h equals 0, implying surfaces with h equals 0 are minimal surfaces.